All right, so we want to talk about the normal distribution. There's some stuff here at the beginning. I want to just show you kind of the theory behind it. So I want to discuss a couple of real brief things here, kind of technical things here that to help you understand what's going on with the normal distribution. First of all, what we were looking at with the binomial probability is what's known as a discrete random variable. In other words, we had the probability of exactly one occurrence or two occurrences or three occurrences or four or so on. When we were doing binomial, we never said, hey, what's the probability that they succeed 3.5 times? You know, because they were discrete. They were separated integers. Okay? The normal distribution is a little different because we're talking about things that are continuous. All right? The variable x, this capital X here, is continuous and it could be any real number. Okay? Also, what this is saying right here, on a continuous distribution, the probability that our random variable x equals any specific number, x, is 0. In other words, the probability at any one exact value is going to be 0. Okay? Because when we're talking about continuous things, we're talking about things that could be measured. And anytime we're measuring things, we're dealing with a limitation based on how precise our measurements can be. For example, if you have a ruler and you're measuring the length of something, it may look like it's exactly 4 inches, but if you were to zoom in and get a more precise tool, maybe you would find that it's 4.01 or maybe 4.0001, okay? We can never be 100% certain that it's exactly 4 inches long. Okay, so the probability that something would be exactly 4 inches would be 0. However, we could find the probability that it's anywhere between, 4.0 and 5. Okay, we can find the probability of different ranges of values. And that's what we'll be doing here as we look at the normal distribution. Okay, another thing I want you to see here is that what we're going to look at is not just some random thing someone made up, okay? It actually is based on a function. It's called the probability density function, and you can see it right here, okay? That's kind of a crazy looking exponential function there, okay? It's 1 over the standard deviation times the square root of 2 pi times e to the negative 1/2 times x minus mu over sigma squared power. Okay? You do not have to know this. Alright? But I'm showing you this because I want you to realize that what we're dealing with, we actually can graph. You know how we're going to sketch the bell curves. You guys have all seen bell curves before. Those bell curves are the graph of this function given a certain mean and standard deviation. Okay, the mu stands for mean, sigma is the standard deviation. Okay, now there is some notation I would like you to be familiar with, and that's this right here. This x, and then you see the little tilde. That means x is distributed normally with a given mean and variance. Okay. Now, as you'll see, we're going to use the standard deviation a whole lot more, but it's given as the variance, all right? So, for example, we could say that x is distributed normally, let's say with a mean of, 83 and a variance of, say, 9, okay? So, in this case here, if that's what we were told, we would say that the mean is what? The mean is 83. And what would our standard deviation be?
Square root
The square root of the variance, so it would be 3. Okay?
I thought you said square.
The square root, okay? Standard deviation is the square root of the variance. And actually, one thing you'll sometimes see here, because they want to help you remember that that's variance, sometimes you might even see this written as x is distributed normally, normally 83, comma, and they'll actually write 3 squared to kind of remind you that that's the variance. And to make it obvious that, hey, the standard deviation is 3. Okay? Yes?
What's the 0? Is that the notation for variance?
No, that's a sigma. It's got that little hat on it there.
Okay.
If it were sigma squared, that would be variance.
So
Okay.
that's standard deviation.
Yes, that's standard deviation. Sigma squared is what's actually shown. That's the 9. Okay? Oh, gee. I don't know why I did that. Okay. So, let's talk about a normal distribution here and actually draw a bell curve, okay? We're not going to draw one for all 3 of these, but I want to show you how we can draw a bell curve, okay? And, if I ask you to sketch one, what you would need to do, okay? First of all, let's just practice with our notation. If we have a mean of 25 and a standard deviation of 5, what would we put for the notation? X,
and tilde.
okay, is distributed.
X is distributed normally with the mean of 25 and variance of 25.
Okay, good. And you can either put 25 here, or if you would prefer, to just write 5 squared to remind yourself that the standard deviation is 5, and that what you see is the variance. You can do that. Okay? Okay, so for part B, we would say X is what? Someone else, what would we have there?
30.
X is
Distributed normally
good, distributed normally.
with a mean of 30 and a standard deviation of 4 or 2 squared.
Okay, good. The variance there is 4 or 2 squared. Okay, very good. And then finally we would have X distributed normally, and what would this one be? 21 and
100.
good, 100 or 10 squared, however you prefer there. Okay? Now, I'm actually going to do letter C here. Okay? I'm going to graph it using this line down here. This is like my x-axis. Okay? This is our x-axis. Our y-axis might be over here. Okay? But you'll notice here, x is distributed normally. Again, we're going to do C. With a mean of 21. Okay? So when you go to sketch these, you want to do... Let me move this over just a tad. You want to first of all put your mean on the graph. There's 21. And that is going to be the highest point on your graph. Okay? One other thing about the normal distribution is that the mean is always equal to the median. Okay? So the mean and the median are the same thing. So that is our mean. And by the way, you saw the mu used earlier. You can use x bar or mu. We're not really distinguishing in this class between the two. But understand if you see this, they're talking about mean as well. Okay? That's the Greek letter mu. Okay?
In what case are the mean and the median the same?
What in a normal distribution, the mean equals the median. Okay. Now, again, if I'm going to sketch this, what I do is I use my standard deviation, and we typically will sketch 3 standard deviations either way. Okay? So I would go 1 standard deviation this way. So here's x bar plus mu, not plus mu, plus sigma. And that would bring me to what value?
31.
What's that?
31.
31. Okay, sigma's 10, so I'm now at 31. And then if I go another standard deviation, that'd take me to x bar plus 2 sigma. So I would be at 41. Okay? And then I would go another standard deviation. And that would put me where? 51. Good. Okay. There's 51. So now we go to the left side as well. We're going to subtract 1, 2, and 3 standard deviations. So x bar minus sigma would equal what?
Isn't it 51?
Yeah, 51.
11.
Let me fix that. Yes, you're right. We would be at 11. Okay? So there's 51, 21. Here's 11. Okay? Then x bar minus 2 sigma, we'd be at 1. And that means that x bar minus 3 sigma, we would be where?
Negative 11.
Well, negative
-1.
negative 9. Okay? For subtracting 10. So that means I need to kind of move my y-axis, don't I?
Yeah, wouldn't that, yeah.
Alright. Whoa, what happened there? Disappeared on me. Okay? So my y-axis would actually be about here. Okay? And that's okay that it is in the negatives. And then let me do this to move it.
So
Okay.
you're doing the mean minus each variant?
Each standard deviation.
Okay.
Okay? Now, the reason why we do that is fewer and fewer of our pieces of data are going to lie at the further standard deviations away. For example, the mean, median, and mode here are all, we're going to assume, at the mean, okay, at 21. There are going to be fewer scores over here, 1 standard deviation away. Okay? So there we are, 1 standard deviation away. Then once we get to 2 standard deviations away, there are even fewer. Okay? But notice it is symmetrical. Okay. And then finally, by the time we get out here to 3 standard deviations away, there's actually very few that are that far away from the mean. Okay? And hence, we have our bell curve. Okay? So you'll notice here, it's really low, then it's rising. It's going to peak here at the mean. And then we've got that right there. Okay? So there's our bell curve, and I'm not a very good artist, but you can see it. All right. Now you might say, well, what good is this, just sketching it? All right. Well, this can tell us a few different things. There are a few observations that we can make. One, you'll notice the majority of our data is actually going to fall within one standard deviation of the mean. Okay, so if we go here and here, notice there's a lot of our data that falls in this range. In fact, there's actually a specific percent of our data that falls in that range. And with a normal distribution, it's actually 68%. Approximately 68%. I think it's actually like 68.13 in a perfect normal distribution. But for us, 68% lies within one standard deviation of the mean. Now, what that also means, this is symmetrical. So if I were to cut this in half, approximately 34% of our data would be on the left side, and approximately 34% of our data would be on the right side within one standard deviation. Yes?
What is the y-axis? Or what thing difference?
Well, remember, we're graphing this, okay? The y value, we don't really use the y value. It's going to vary. It's essentially the probability. Okay, it's the probability. But actually, if you were to graph that probability density function that I showed you, you'd have to zoom in until like your y-axis was going like from 0 to 0.4 or something like that in order to even see the curve. So it's very, very small. But then we can also see another thing here. We have within two standard deviations, you'll notice we have 95% of our data. Okay, you can see that here on the right-hand side as well. That was the distribution A. Notice the mean was 25 and the standard deviation was 5 in that case. Okay, in our example here, we have, I'll use this. Here's two standard deviations below and two standard deviations above. So 95% of our data falls into this range from 1 up to 41. Now what that means, remember we called this a probability density function. If I were to pick a random piece of data, I'd have a 95% chance that it's going to be somewhere between 1 and 41. I would have a 68% chance that it fell somewhere between 11 and 31. Okay? You see how this is working?
So then can you subtract 68 from 95, divide that by 2 and put each in one section?
Yes. Okay? And that actually turns out 95 minus 68 is going to be 27. So divided by 2, you're right, there would be 13.5% between the first and second standard deviations. Okay? And then finally, we have the third standard deviation. Okay? If we go all the way out to the third standard deviation, as you can see down here, the mean plus or minus 3 standard deviations is 99.7%. So what that means here is that 99.7% of our data lies between -9 and 51. Okay? All right, so if you think about this here, guys, all right, we can state this in terms of the probabilities, okay? the probability that a random variable is going to be between -9, and it could be less than or equal to or less than, because remember the probability of an exact point is 0, so it doesn't make any difference. So the probability we're between -9 and 51 would equal what?
99.7.
99.7%, okay?
How did you get that? Oh.
From right here, okay? Within 3 standard deviations is 99.7% of our data, so the probability that a randomly picked value is going to be in that range is 90.997. Okay? The probability that we are between 1 and 41 is what?
95.
95%, okay? And the probability that we're between 11 and 31 would be what?
68.
Good, 68%. Okay? All right, does that make sense? Okay. I don't want you to lose the fact that these are probabilities, okay? And you might say, where did these come from? All right? This part you're not going to have to do, but it actually comes from calculus. Okay? You know that function I showed you already? The real ugly one?
One on top of the view.
The 1 over sigma times the square root of 2 pi times e to the that mess?
Yeah.
Okay. If you take the integral,
What does that mean?
it's a calculus thing, it's finding the area under the curve. If I found the area underneath this curve, if I were to graph it,
Yeah.
and I used an integral to find the area would be 0.68 from 11 to 31. We're actually going to learn how to use your calculators on Monday
Show us that.
to show you that, but we're not going to even have to graph it. Your calculator has it built in. It's really cool. All right? So, let's take a look at this. Just a quick question here. What effect does the standard deviation have on the curve? You'll notice back here the standard deviation was 5. Here the standard deviation, not x. The standard deviation was 10. And here the standard deviation was 2. So what effect does that have on our curve?
The width.
Yeah, the width. It's going to be spread out wider the bigger your standard deviation is. And that makes sense, right? Standard deviation is spread of the data. It's a measurement of spread. So a bigger standard deviation is going to have a more spread out curve. Here with the standard deviation of 2, okay, notice it's really bunched up here in the middle. Everything is really close to the middle. Okay?
So you can just count between each to see the standard deviation.
If it's already drawn, yes. If you're told what those are, yes. Typically, you'll be told, you'd be instead told, this up here and have to draw the curve yourself. Okay? All right. So that's it. Okay? That's it. As far as the introduction to the normal distribution. Okay? Let's just, yeah, we have time. Let's just try one here real quick with this number 4, okay? It says the mean height of the players is 184 centimeters. The standard deviation is 5, okay? So let's put our 184 here. And 1, 2, 3, 1, 2, 3. Okay. As I go to the right, what's the next number going to be?
189.
Good, 189. My standard deviation is 5, right?
Yes.
So x is distributed normally 184, 5 squared. Alright, so I have 84, 189, the next one is,
194.
good, 194, and then finally,
199.
199, okay? So now, somebody else going to the left. From 184 down 1 standard deviation would be,
179.
good, 179, then,
174,
good, and finally,
169.
169. Good. All right. So to sketch it, put a point there at the top at the mean, 2 points at about equal height, 1 standard deviation away, then 2 standard deviations away, we have another 2 points at equal heights, and then 3 standard deviations away, we're getting pretty low. All right. So then you can sketch your bell curve.
How do you know how far down and up to put those dots?
It's just an approximation.
Okay.
The main thing is you're identifying those boundaries. Okay? And remember our numbers are 68, 95, and 99.7. Okay? If you can remember those 3 numbers, then you can fill in and figure out these probabilities. Okay? So a real quick question here. What's the probability that we pick a person and they're taller than 184? What's the probability that they're taller than the mean?
0.
1/2. Okay? So now let's use this 68%. We said it's going to be 34 on either side, right? 34%, 34%. So then part A, what's the probability that a random person we select is greater than 189 centimeters? How would we figure that out?
That would be 16%.
It would be 16%, okay? Check this out, guys. We're looking for, whoa, that's way too big. Hang on. Let's do that. We're looking for this area, okay? Under the curve. All right? We already said that to be above the mean has a 50% chance. So, it would be 50 minus the 34. Very good, okay? So 0.5 minus 0.34, we've got a 16% chance of being taller than 189 centimeters. Okay? Does that make sense? Okay? How about taller than 179? Probability X is greater than 179.
84.
Very good, good. It's more than half. In this case, we're finding the area from here all the way to the right. So that's going to be the half plus this 34% to the left. So that's 0.84. Okay? And now you can find different variations of these as well. We already identified this would be 13.5%. This would be 13.5%. The difference between 95 and 99.7 is 4.7. So each of these would be 2.35%, right? 2.35%. Okay? If you figure those out, then all of these are pretty simple to figure out. Okay? So the probability that X is between 174 and 199. Okay? Well, 174 to 194 is how much? What's the percentage from 174 to 194? That's 95. That's 2 standard deviations, right? So that's the 0.95. But then we need to add that extra, this part in extra. So it's plus another 2.35%. Okay? All right? Now, I will say, we're using a pretty specific value here. This 99.7% is what's used like in AP Stats and in IB. Okay? If you're looking online, you may see people write it, they just round it kind of to 99.5. Okay? The principles are still the same. All right? But just be aware of that. Okay? All right. So, that's it for that. Well, let's think about D. If I wanted to be over 199, let me switch colors here. The probability that X is over 199, that means I'm finding this area to the right here, right? Mm-hmm. And this goes on forever, by the way. The x-axis is an asymptote. All right, so I'm finding that area. So what do you think we could do?
From 50 subtract 34 plus 13.5 plus 2.5.
Yeah, that's a good idea. We know everything to the right of 184 is 50. So if we did that 0.5 minus these three combined, we'll get the result. So let's see.
It's 49.85. Somebody double checking that.
I believe that's right, yeah. Because there's actually another way you can do it even too. All right, so we get 0.0015. 0.15%.
So you're probably not going to get that.
Okay? Now, here's another way you could have done this, is to notice, hey, 3 standard deviations is 99.7. So that last 0.3% is this side over here and this side over here.
Oh,
So if you divide the 0.3% by 2, you get 0.15%. Okay? But either way works. Great.
Thank you.
Okay?